So I want to talk a little bit about the sort of typical approaches we look at in sort of the computing and signal processing classically when we talk about analog systems. And it's kind of important because for the most part when people think analog systems, classically it pretty much falls along this very simple perspective of I'm going to have some low noise amplifier, maybe some other sort of front end components. I'm going to have some signal conditioning, which might be a demodulation stage. It could be a couple various things, could be some filtering, and then usually a data converter, and then I get that result into digital as fast as I can, because that's where I've got programmable and configurable things, and I can have code and I can have modularity, and that's how we usually look at the world. So classically what this typically means is there's going to be some inputs to this, input or inputs. There's usually some pre-processing, often something like LNAs or to get something up out of the noise, to get a small signal to something reasonable. Again, think everything is about how do I get decent data conversion and get it to my digital system. This is the way we think about it classically. And so usually that's going to result in some sort of filtering state, pre-processing some sort of filtering stage. Then we do a sample and hold, which samples things. And then there's usually an ADC in the block. And typically when we talk about a data converter, you're going to usually put the sample and hold in the data converter. There may in fact be some of the pre-filtering that may need to be part of it as well. And you might ask, well, why would I do this? And this is sort of a nice picture, and I will give credit to, came out of Phil Allen's notes when we were actually co-teaching classes together at Georgia Tech. This is a really nice perspective of, just thinking about this is your continuous sort of frequency response of something. When you sample it, what happens? Well, I effectively modulate it in multiple frequency spaces. If you think about it, you're convolving it with a whole comb filter set. And so if I can guarantee it's band limited at some place and I space it further than that, then life is good, right? Now the problem is if I get too tight in the frequency, then all of a sudden I got these various frequency components combined, and it's hard for me to separate them out. And this is what's typically called aliasing. Well, here's the thing that you typically try to do with this filter is you try to make sure that I put some sort of block on here that guarantees, even if it is some sort of bandwidth structure, that I can guarantee that I cut it off. And so this makes sense. And nice theory, you say, let me assume I have a nice hard wall filter. The problem is you don't get that. The problem is you actually have to build it, and there's some transition region. And the tighter the transition region, the more expensive, the higher order, the higher the Q, all of that for that filter. So this is why practically you usually want to back off a bit of this. This is why, although Nyquist says twice, you go twice the frequency and you're fine, in reality you actually give yourself more room than that to actually make reasonable anti-aliasing filters. So that has to be there. Then there's the sample and hold, which then expands everything, and then it's the ADC, and the whole reason is that when you put it in the digital system, you can actually deal with the signal that you're working with. And so the key is to remember that there is some spacing here in practical terms. You have to have it. If you're actually having to design that filter, you know how important that spacing is. Now, I also want to make a small tangent in this because it turns out going forward that this classical picture in architecture is getting changed, and we're beginning to start to see things that are different architectures, where we're realizing that I can have programmable analog, I can have programmable systems, I can do computing in the analog side, and that starts to change the fact that these things now start to become part of the analog computing, completely changes this perspective, because now you think, well, wait a minute, I'm not worried about the anti-aliasing in the same way, because now maybe when I'm converting things, it's already classified. And a classifier is just a simple form of a data converter, or data converters is one form of a classifier. And all of that now moves into the digital system, which may do computing, if symbolic or not, and other kinds of computation. And that will change this picture. And yet, if you're dealing with a very classical sort of front-end system, these are the constraints you typically deal with. This is the entirety of analog architecture classically. And this is entirely of what you typically need to do when you're looking at the data converter and its implications that you're building around it.